The archivist here at the Railroaders Memorial Museum, and I want to thank you for coming this evening to our second lecture in our Along the Broadway series. This is one of many lectures that will continue throughout the year up until November. So we're very lucky to have that many speakers, and of course your contribution and your attendance to this supports the museum's mission, so I thank you for that. Bathrooms are right outside here to your left. And then, of course, if you're thirsty or need anything to snack on, we have our concession area open as well. And with that, I'll go ahead and introduce our speaker, although I'm sure many of you already know Mark, but I got a little write-up here on him. After graduation from the University of Pittsburgh in 1977, Mark Glenn joined Gwynn, Dobson, and Foreman as a civil engineer. A native of Corsica, PA, Glenn became president of the firm in 1985, a position he still holds today. His historical interests include the area's legacy industries, infrastructure, and the individuals who created them. Glenn is a registered professional engineer. So if you have any engineering questions, I'm sure he'll be happy to answer them. And with that, Mark, the stage is yours. Thank you, everybody.
Thank you. Well, thank you for coming. I have a brief intro to our presentation tonight, which is Charles B. Dudley, Ph.D., who is the PRR Altoona Scientist to the Nation. When you hear people talk of the PRR, you inevitably hear that it was the standard railroad of the world. And in terms of what that meant at the time, varied. Usually in a big picture sense, it was more of they're the biggest and the wealthiest industry in the country. They have the longest railroad. They have the best managed system. They have a lot of technology in play in the service to thousands of passenger customers and the largest freight traffic in the world. The gentleman that I'm going to talk about tonight really was the person that put the standard into the standard railroad of the world in a literal sense. And I'll talk about that later. But Dudley was a very unique individual who had a lot of life experiences even before he went to college. And on that note, I would like to move on to his upbringing and early education. Charles Dudley was born in 1842 to parents of New England ancestry in Chenango County, New York. He was raised on a farm and attended school at the nearby Oxford Academy for primary and secondary education. Because of his academic achievements, Dudley looked forward to going to college and then a rare opportunity at that time for a rural youth. In 1862, at the age of 20, Dudley enlisted as a private in the 114th New York Volunteers of the Union Army. During the following 3 years, he took part in 7 engagements. Several involved battles. Most were in station in occupation. However, in 1864, the regiment was assigned to the Army of Shenandoah, created by Ulysses S. Grant under the command of General Phil Sheridan. He was the famous cavalry officer on Sherman's march through Georgia. This army of 39,300 soldiers was ordered by Grant to defeat the Confederate Army and thus eliminating the threat to Washington, D.C. and the North. And you can see Sheridan, the above picture, and his adversary, Jubal Early of the Army of the Valley. So the 114th Regiment was involved in the largest and bloodiest engagement in the Shenandoah Valley during the Civil War. On September 19, 1864, at the Third Battle of Winchester, 54,000 soldiers fought and resulted in 8,600 casualties sustained, more than the combined total of all previous battles in the valley. The 114th New York Volunteers saw the heaviest action and sustained the most casualties of any unit in that battle. Its brigade was ordered to block a Confederate attempt to flank the Union Army on the right over an open field. The 114th suffered the most, as many soldiers were cut down within 10 minutes on the march. Casualties were high. The regiment sustained 188 dead and wounded out of 350 engaged, a very high casualty rate. Charles Dudley was one of these severely wounded. Dudley was wounded in the leg, and the wound was so bad that doctors decided that they were going to leave the bullet intact and not have to amputate his leg. However, varying reports said that was a disability that impacted him and the rest of his life. Others said that he was severely wounded. So many who fought at Gettysburg said the fighting in this battle was among the fiercest of the entire war. In the end, the Confederates were defeated, which marked the beginning of the end for the Shenandoah Valley as a supply route and army corridor for the Confederates. To ensure compliance, General Sheridan initiated a scorched earth campaign that fall, setting 2,000 barns, mills, and crops on fire from one end of the valley to the other. Let me see here. So basically, Dudley had a crossroads in his life when he, in the aftermath of that battle, because he was severely wounding and was pondering his future. One thing was certain: his days as a soldier were over. Dudley was discharged from the Union Army in 1865. During his convalescence, like many of the returning wounded, his physical and mental condition may have precluded an active life. However, Dudley spoke no more of this life as a soldier and resolved to pursue college and a career where all his efforts were applied. He returned to Oxford Academy and worked to earn money for the next destination in his life, Yale University in New Haven, Connecticut. Now, Yale at the time was considered probably the premier academic program for science and engineering in 19th century America. Part of that reputation came from its affiliated school in terms of location and curriculum, meaning the Sheffield Scientific School. This chemistry program at Sheffield Scientific was foremost in terms of faculty, academic rigor, and scientific innovation. Yale was the first university to offer a science-related graduate program and to award the first Ph.D. in the United States. Now you can see some of the faculty members in the lower border of this slide in North Sheffield Hall, which was the main academic building. I could call your attention to the person in the middle, the third from the left, Benjamin Silliman. Now he and his father were responsible for creation of the chemistry department, but he also was one that evaluated geology and mineral deposits. And he was approached by a group of New York investors to evaluate a potential source of rock oil in Pennsylvania. And they needed a geologic report in order to satisfy the investors. So he traveled to the site, did a study, and said that rock oil would be a good source of illuminating oil for instead of whale oil for that purpose. So he recommended that be explored. So it fell to a driller from Titusville, Pennsylvania by the name of Colonel Drake, who drilled the first well, and also the rest is history. Silliman was also responsible for distillation of petroleum products, which was a major breakthrough in refining. And he also was a vital part of the faculty. Now, the other person worth noting is Josiah Gibbs. He was this first Ph.D. that was awarded by Yale, second from the left. And he had a very interesting career. He was a child prodigy, attended Yale, graduated when he was 18, and was awarded a Ph.D. Now, his chemistry was of the type that was significantly more research-oriented and scientific than some of the other faculty members. In fact, so scientific that none of them could really understand his rationale. His big topic was thermodynamics, of which he was a founding father in that category. Albert Einstein said that Gibbs had the finest mind of any American in history, and he was not appreciated until the 20th century for his work in the field. But those were the faculty members that Dudley was exposed to during his tenure at school. So in 1867, he decides to enroll at Yale, limited money, had to work his way through his undergrad program. He started out as a freshman at age 25. He was a member of the class of 1871, having served his country as a wounded warrior, and was from a rural area in upstate New York, which was a bit of a oddity for students at that time, most of whom came from the Atlantic seaboard area. His classmates had no exposure to battle and regarded Dudley's mature, considerate, and self-effacing manner as highly respected by his classmates, who affectionately called him Pater Dudley or Father Dudley. He earned a Bachelor of Arts degree in 1871 and was elected Phi Beta Kappa that year. He gave a commencement address at the 1871 graduation ceremonies. To earn money for the doctorate program, he took a year off and became a night editor of the Yale Current newspaper. Having sufficient funds, he attended then the next 2 years of rigorous study in the doctorate program. He earned a Ph.D. in chemistry and was the only Ph.D. candidate from Sheffield Scientific in 1874. After passage of many years, a classmate recalled, "As I look back at Dudley, at all his characteristics, he seems to have been an Abraham Lincoln sort of man, a type of manhood of which American citizenship cannot be too proud." So at the age of 32, Dudley embarked on his career as a physics professor at the University of Pennsylvania. By perseverance and all odds, he overcame his obstacles to attain academic excellence. So we're going to move for a brief description of a person that had a significant impact in his career at the Pennsylvania Railroad. And that gentleman was went by the name of Theodore Ely. And he had started work for the railroad in 1868, but quickly became the superintendent of motive power for PRR Altoona. And what that means is that was a very high position, one of the highest that could be attained at the Altoona Works. He was a leading U.S. railroad engineer and executive in this position. And during his 42-year career, Ely transformed the PRR Altoona Works into the largest and most technologically advanced railroad and locomotive complex in the United States. As an engineer, Ely's refined locomotive design became an industry standard in 1883. By moving the firebox and boiler assembly over the larger drive wheels, his design allowed for bigger and more powerful locomotives. And in 1890, Ely also completed the Juniata Locomotive Works solely for fitting and erecting these larger locomotives. Now here, just for reference purposes, is the steam locomotive that he had designed. And you can see by the long boiler at the front of the locomotive, and of a much larger diameter than previous locomotives. Well, what resulted was more wheels meant a longer boiler and a larger diameter boiler, something you would see on the big freight trains of the railroad in the early 20th century. So this man not only had engineering expertise, but he had a mechanical mind too. So one of Ely's first acts as superintendent of motor power at the Altoona Works was to create a test department. And the selection of a chief chemist was the next step. So upon the strong recommendations of a prominent 19th century mechanical engineer and Penn physicist, Dr. George Barker, Ely offered the position to Charles Dudley. He accepted the position in late 1875 at age 33. So he was tasked with creating what later became the foremost industrial research lab in the country. And his labors were all done in this building, in the Master Mechanics building, from 1882 to 1914, which was the bulk of his career. It may seem odd that the PRR would entrust a recent graduate student with so much responsibility. But Dudley had 10 years of real-world experience as a soldier, scholar, and researcher. He was mature, wise beyond his years, and had shown leadership qualities. And this long interval in his life and his education as a soldier proved really valuable experience for the high position of PRR Chief Chemist. So now we're going to direct our attention to a topic that had gotten the attention of the Pennsylvania Railroad and Thomas Ely in particular. That was the steel industry and the making of steel rails. Now, the steel industry emerged after the Civil War by introduction of the Bessemer steel process. Essentially, high-pressure air was forced into a molten pig iron vessel, as you can see in the lower right. This step oxidized and drove off impurities such as carbon, silicone, and manganese, known as slag. It also raised the melt temperature to above 1600 degrees Fahrenheit, which was critical to the process. So when you hear the name blast furnace, that was the forced air process that we are referring to here. So a pear-shaped ladle poured the molten metal into ingots, which later were reheated to form steel beams, rails, bars, pipe, and other shapes. Steel was more durable, stronger, and economical than iron, and made possible creation of longer bridges, taller buildings, pressurized pipes, and reinforced concrete, to name a few. The major source of steel rails were three places in Pennsylvania: Cambria Iron Works in Johnstown, which was the location of the first steel rail fabricated in 1857. The Carnegie Steel Works in Braddock, PA, the Edgar Thomson Works, and the Pennsylvania Steel Company in Steelton, PA, outside of Harrisburg. Now, the top figure is the Edgar Thomson Works, and that was by far the largest steel plant in the world. And by 1904, production there had increased from 32,000 tons of steel in 1875 to over 70,000 tons per year in the latter decade. The person in the upper right-hand corner was the famous Bessemer steel expert, Captain Bill Jones, who was a mill manager and ran the mills at both Cambria and Carnegie Steel Works. In terms of steel, though, there were problems of a standard of quality nature in the steel process. Steel was significantly more durable, but this period was plagued by technological challenges and excessive material failures, causing numerous, often deadly and catastrophic derailments. Early steel rails, which replaced the less durable wrought iron, were prone to what's called brittle fractures under cold conditions or excessive train loading. By 1880, there was an average of 8,200 train accidents per year, including collisions and derailments. Now, aside from public safety, the Pennsylvania Railroad was concerned about the frequency of broken rails, the related costs of rail replacements, the removal of derailed trains, and interruption of train schedules. That cost money. And this situation also resulted in the catastrophic disasters involving train derailments from that era. And I'm going to, for less illustrative purposes only, provide a description of the West Hartford, Vermont bridge disaster. Now, this disaster occurred on February 5th, 1887, when the Montreal Express train derailed on a bridge over the frozen White River in Vermont. A broken rail before the bridge caused rear passenger cars to plunge 40 to 70 feet onto the ice, where overturned coal stoves ignited a fire that killed 38 trapped people and injured 50 more. The resulting fire completely engulfed the wooden bridge and train, and as you can see by the middle picture on top, there is nothing left other than the stone piers of the bridge. Now, bitterly cold temperatures of minus 20 degrees Fahrenheit, metal fatigue, high train speed, and defective rails contributed to a sudden brittle failure and derailment of the train. The Dean of Engineering at Dartmouth College in New Hampshire inspected the accident site and recovered the broken rails for examination. A slag seam in the rail section at the right-hand side of this slide was the major cause of rail failure and indicative of poor manufacturing and lack of quality control. So what he is referring to here is this this section of the shadow here in the rail is the slag deposit that was in this rail. Now, slag is a contaminant, and really it was just only a matter of time before there was going to be a derailment, and it couldn't have been at the worst possible location at the worst possible time. So it was accidents like this, and there were many of this type, that caused the PRR to study steel rails. And the principal cause of train derailments became the focus of Charles Dudley's research from the beginning of his tenure. In his study, he applied unprecedented methods of analyzing the physical and chemical properties of broken samples of steel rails and subjecting them to thorough testing to validate assumptions and conclusions. Now, I don't want to get too technical here, but I do want to highlight several things that Dudley did with this study, including compiling data on rail sections, including locations of derailed and broken tracks, length of service, gross train tonnage, and sketches of the rail section as shown in this detail in the slide. Let me pull it over here once. A chemical analysis of broken steel rails along with physical tests for bending, breaking, and pulling were undertaken. The data was compiled and evaluated in these tables that are shown in the upper right-hand corner. So what he concluded was that steel of higher carbon content was stronger but lacked the ductility or bending, so to speak, of lower carbon content steel. He developed a standard of quality in the form of specifications that listed the required chemical parameters and bending tests. This allowed for competitive bidding while setting quality standards for the rails. Now, what was interesting about this was Dudley prioritized data analysis over conventional wisdom and rule of thumb methods that existed at the time. Data collection, evaluation, testing, research, reevaluation, validation, conclusions, all aspects of his approach that later became collectively known as the scientific method. Dudley's scientific approach in his steel rails evaluation was a master's class in applied science. So, with every action, there's an equal and opposite reaction. And that, of course, sent the steel industry into a bit of a panic and sent shockwaves through the industry. They were concerned about the implications of Dudley's study, but they were resistant to any criticisms of their steel and were determined to retain full authority over quality control. They regarded academics like Dudley as outsiders in their chemistry labs having no practical application. In effect, they stood above all as a vanguard of a second industrial revolution and a driving force in the country's growth. Now, the people that were involved in this study were actual leaders in criticism of Dudley's work. And matters came to a head at an American Institute of Mining Engineer conference in Baltimore in 1879. Knowing Dudley was going to be present to defend his report, steel company representatives and academics dissented. Basically, their objections included insufficient number of samples to make a judgment. There were other chemical factors. There was a molecular structure. There was ingot cooling. You name it, there were other reasons. Many had technical data to bolster their cases, but none were published like Dudley's that addressed an urgent need. Now, the people in this top row were primarily academics. There were several engineers that did consulting work in the steel industry and in the Bessemer process. And there was a representative of Captain Jones was there, and also a William Shin representing Carnegie Steel. However, they were somewhat, shall we say, resistant and patronized Dudley's work as a good first attempt by a young chemist. However, it reminded them of French metallurgists, which we took to mean is not a compliment. Dudley's response, they said that they made the best rails, and any changes to their process would wait for better research. So Dudley's response, and he was quoted in this, was, quote, "Indeed, proceed with more research. Meantime, Pennsylvania Railroad will insist that rails be made to its specifications, as our research and experience have shown will provide a better rail." Now, this stunning rebuttal to Captain Jones from a young chemist was had the imprint of Theodore Ely, who was Dudley's patron. The established fact was the PRR would not accept defective steel, even if legitimate metallurgical concerns existed. Since the Pennsylvania Railroad was Carnegie Steel's biggest customer, they complied with Dudley's specifications, one that became the PRR standard for 30 years. Andrew Carnegie, not Captain Bill Jones or William Shin, made that decision. So what did Dudley learn from this process? Well, it wasn't what you expect to learn, that he would be reacting to criticism and had an intention to prove people wrong. He saw it the other way. Now, at this meeting, Dudley made a conscious effort to assemble people, including scientists and industry leaders, for their viewpoints. And most of these people, as I said, expressed doubts and criticisms of his work. But these participants also provided data from their research that had been developed and from real-world experience in the steel-making process. So after the Baltimore meeting, a kind of synergism developed that created even more research into the field of steel rails from those attending and other industry professionals alike. Dudley thus became an advocate of collaboration involving scientific-based research with manufacturing input. That goal was to develop industry-wide standards of quality through specifications. Little did Dudley know that his concept had application far into the future for all types of manufactured products. Now, Dudley ran the chemistry lab at the PRR for 35 years until his death in 1909. And you may ask, what was his research and what were the specifications? And I have a listing here of the various items they evaluated, but this is just a very brief list. There was a tremendous amount of research done that came out of this lab, and he published it. He published it in technical journals, so all people who read it, including other steel companies and their engineers, read it. And the goal was to create a common specification, a common viewpoint and standard of quality, whereby they would be getting the best product for the money. And there are literally hundreds of these type of reports that exist in the public record from that era. Now, just as a result, here's a listing of some of Dudley's patents. on the left-hand side. I'm not going to go into detail on those. And then there's some papers that he presented on chemical methods in terms of how certain measurements were made of certain products like silicone and steel, copper and lead and phosphor bronze, ammonia and ammonium chloride. Just a very brief sampling of his work, a lot of which was developed and written by him and his assistants. So in terms of who worked there and what their responsibilities were, all the chief chemists that were employed by the Pennsylvania Railroad and elevated to that position had a lot of academic training. And that's another thing that set the PRR apart in terms of standard railroad of the world. They hired the best people. And the fact is the best people wanted to come to Altoona to work, not only for Dudley, but the whole physical test department that designed and tested locomotives was a huge draw. But just for the chief chemists, Dudley was the first person, was there 35 years. But his assistant, Frederick Peace, was also a Ph.D. from Yale, who then assumed control of the department from 1910 to 1921, including the new test plant building on 16th Street. Then we had a Milton McDonald, who got a Ph.D. from Penn State in chemistry. He had control of the department through August 1st of 1943. So we're seeing almost 75 years of a Ph.D. involved in one of the most critical positions in terms of testing and analysis. We have another person, Thomas Fisher, was from Tyrone. He attended Princeton. And he also was instrumental up until 1947. And then the remaining two closed out the test plant era at that time. The test labs here were considered one of the premier industrial labs in the U.S., if not the world. In fact, the test plant welcomed railroad chemists to study at the test plant, including those from Russia, Germany, England, Japan, Australia, France, among others. So as I mentioned, the chemical test lab attracted the best and brightest. And the scientists were largely recruited from elite universities in northeastern U.S. and technical skills who wanted to work for its eminent foundational leader, Dr. Charles Dudley. In the 1900 to 1910 era, of the 27 test plant employees, 23 were chemistry graduates. And here we have an organization chart showing the various jobs of 62 employees, including 43 chemists that were employed during World War I. As you can see, the lab expanded greatly, showing a multitude of analysis performed. Also part of this team were teams of inspectors who visited manufacturers and performed or witnessed compliance testing at the plant site. Now, my wife's uncle and my grandson's great-great uncle was one of these inspectors. His name was George Ehrenberg. And he was an apprenticed individual who became part of the test lab in his apprenticeship. And then after that, he spent the next 45 years of being a steel inspector. And he would travel to sites all over the eastern United States, in Birmingham, Gary, Indiana, Sparrows Point near Baltimore, Bethlehem Steel near Bethlehem, the plants on the Monongahela River, you name it. He was to these sites where he would verify and document compliance with the specifications and even do testing when he was there to make sure they got what they paid for. And nothing was shipped until the inspector approved and had it countersigned, signed by someone back at the test department. So in 1914, the new test plant was built at 16th Street and Margaret Avenue. And this plant was constructed on the west side of the PRR Altoona works. The fireproof building was constructed of reinforced concrete with brick facade, with 4 floors and over 30,000 feet of space. The chemical labs occupied the third and fourth floors and rooftop area. We believe that planning and design for this building had begun when Charles Dudley was living. So you can see in the bottom portion the construction work, and basically all the form work and beams there were of concrete, including the columns. The upper right-hand picture is a picture in the distance of the building, and these are the stores where the axles and wheels and everything were stored for later fabrication and erection in the plant. So just to give you an idea of what the floor plans looked like, this is a third floor plan. The right-hand side was the electrical laboratory. The left-hand side had labs for bacteriological laboratory for water contamination. There was a water analysis lab for boiler feed water, for drinking water. There was a oil, coal, and rubber lab that did nothing but test coal and oil for conformance with specifications. And then the fourth floor, on the next page, is where most of the lab work was done. In this particular case, there were 38 lab benches that were constantly testing all sorts of various products and samples. And also on the roof, the chemistry lab had exposure racks where things were exposed to the weather to see corrosion impacts. Also a meteorological station, more on that later, battery storage, and a photo exposure room. So in terms of chemistry, this lab was the most advanced in the United States and the world. So here's some pictures of some of the labs, and I regret some of the quality here, but you can tell in the chemical laboratory for metals and bacteriological samples and the laboratory involved in that process. Also, here's a water laboratory for drinking water and boiler feed water, which was really critical, especially in the boilers of the steam engines. And also a rubber lab. I don't know exactly what went on there, but there were tests. And here we have a mobile lab. The PRR outfitted a laboratory car that would be taken into, for instance, a steel mill, and then tests performed in that lab car to save time. Now, over a period of time, most of the steel companies had their own test labs. They finally got the message that that's what they needed to do. So, nothing about the test plant can go unmentioned without reference to the locomotive test stand, where locomotives were run at full speed and under varying loads. Nothing like it in the world. This test track was the only one of its kind and was designed as a PRR exhibit at the St. Louis Exposition in 1904. When the exposition ended, the test track was shipped back to Altoona and installed in the locomotive test building at the PRR's test plant. Now, these photos are from the early 1900s, but there are pictures of just mammoth freight engines on this test rack. And I think a recollection of a person that worked for the East Altoona Roundhouse area, Mr. Dale McCracken, was quoted in Altoona Railfan website that, quote, "Only the best engineers and firemen were ever assigned to the test track to operate locomotives undergoing tests. Many engineers vied for this position, for the man thus assigned was considered the best in his field." One of the last locomotives tested on the rack was the experimental class Q2, which showed a maximum horsepower of 7,900 horsepower, running at speeds of 57 miles per hour. This was the greatest horsepower ever developed by any locomotive at that speed. However, many locomotive tests were run at speeds of 100 miles an hour, and the plume of smoke from the building's ventilation chimney was a familiar sight to Altoonans, as was the roar coming from the structure. Mechanical engineers flocked to the PRR in Altoona, as the PRR was the leader in the design of the most technologically advanced wonder of the 19th century, the steam locomotive. The owner of the house in which we live, in which I live, had engineering textbooks in the basement when we bought the house. I found out later that engineer was Wallace Shirley, the PRR master mechanic of the PRR Altoona works during World War II. He was from New Jersey and went to the Stevens Institute as a mechanical engineer. So what we can see here is that the test plant was not only a part of the Altoona works, it was separate, for instance, from the machine shops, the car shops, Juniata Locomotive Works, South Altoona Foundry. The test department solely reported to the superintendent of motor power. So, after the Penn Central merger and during the city redevelopment, many PRR buildings were raised in what was an industrial liquidation and clearance sale. Now, on the right-hand side, we're seeing demolition with a wrecking ball. And a newspaper article was written at the time that said the superintendent of the demolition work said they needed a bigger ball. The ball at that time was 5 tons. They needed a 10-ton ball to knock this thing down. And according to people that obviously were there at the time, said it took most of the fall for this to happen, to bring this building down. And anyway, among the most notable historic losses to the city were not only this building, but also the locomotive test rack, and the engine and car shops of the PRR. The test plant and the locomotive rack really were museum level quality. The amount of equipment and measurement devices in those buildings was beyond belief. There were millions of dollars spent in not only buying the equipment, but having them serviced and replaced from time to time. Where all that went, I have no idea, but it certainly was of a museum level quality. The loss of these buildings was painful for many PRR workers and residents in Altoona, much as the demolition of the Grand Pennsylvania station was to New York City residents in the early 1960s. So, moving ahead, getting back to Charles Dudley, he had a very close relationship with the city of Altoona. Upon arrival in the city, he became active in the affairs of the growing city of Altoona. His participation included matters of health and safety, public water supply, sanitation and sewers, library, among others. Also, over time, Dudley was asked to offer an opinion on a wide variety of topics, from the weather to prospecting for oil. If questions arose of any type, the answer usually was, "Ask Dudley." He was a very unique individual, and one that just wanted to be involved in the community where he lived, and had a real love for the town and the area. But just some of the things that he did for the city: he was Department of the Board of Public Health president. He was the chairman of the Master Mechanics Library and Reading Room. Created and operated Altoona's first weather station at the roof of this building. Public lectures, member of the Altoona Board of Trade, and member of several boards of directors for banks and loan associations. Now, just a brief discussion about the Master Mechanic, or the Mechanics Library. This was a pet project of Dudley, because he thought that would educate some of the railroad workers that could not afford a college education, but could go into the library and read books and journals of a technical nature. Upon the time of his death, he was a member of the board of directors for 30 years. He was head of the library committee. He oversaw the selection of books and technical journals. The number of volumes of library books increased from 35,000 to 55,000 volumes over his tenure. And later, in 1926, the Mechanics Library became the Altoona Public Library with the volumes stored at Altoona High School. This building was the former Presbyterian Church at 11th Avenue and 12th Street. He was also involved in many professional organizations, and his fame grew not only across the U.S. but internationally. He had a wide reputation as being one of the top scientists of the 19th century. And he was asked to join various societies like the Association or the American Society of Testing Materials, mining engineers, professional engineers, the American Chemical Society, and the Pennsylvania State Association of Master House Painters and Decorators. Now that is not a joke, really. There was such an organization, and these guys just loved Dudley because he really got into every aspect of paint as part of his job for the railroad. And I'm talking about pigments and content and all the chemistry involved in paint. Now these guys liked it because he was constantly specifying, a higher level of quality. And so many times these painters who did house painting and things like that got inferior paint that never held up. It was Dudley who was one of the main driving force of improving paint quality in this country. So hence, the master house painter and decorators did appreciate his efforts. And there's a number of colleges here listed where he gave selected lectures for many students at the time. He did give a lecture I did read at Lehigh University where the big topic was lubrication, a topic so important that lubrication became so expensive and had to work because the locomotives were an essentially a motive power device that required lots of grease and oil, and it had to be the right greases and oils. So that was a big topic at the time, believe it or not. So in terms of home life, Dudley worked all the time. He was either working in the lab, working at home doing papers, traveling to seminars or conferences, and really was the apostle of standardization and quality control. Unlike many PRR Altoona people who retired, he did not move to the PRR enclave in Bryn Mawr on the main line near Philadelphia, and he did not retire. Altoona was where he lived, worked, and died. He was as much as part of the community as any native birth person who grew up in Altoona. He did have a house at 802 Lexington Avenue, and you can see it in the upper right-hand corner. And that house was placed on the historic Federal Register of Historic Places in 1976. 1999, it was demolished for a parking lot and taken off the list. Anyway, Dudley in later life found a soulmate. Mary Virginia Crawford was an 1896 graduate of Bryn Mawr College and active in social circles there. She married Dudley in 1906 at the age of 38. After Charles's death 3.5 years later, she moved back to Bryn Mawr from Altoona and was a teacher of history and political economy in Miss Baldwin School for Girls. It's now known as the Baldwin School. She never remarried and died in 1940. So Dr. Dudley died on December 21, 1909, at his home on Lexington Avenue of pneumonia with a typhoid complication. Daily papers in Altoona, which there were 3 at the time, had kept a daily vigil with updates on his condition in the morning and afternoon editions. It was reported that the PRR arranged special trains to transport his wife from New York City with a prominent Philadelphia doctor to be at Dudley's bedside. All attempts failed. One wonders if a strenuous life of constant labors, made worse by the pain of his Civil War wounds, had taken a toll on Dudley. Later photographs certainly showed a man who visibly aged in later life. Funeral services were held in Altoona and Bryn Mawr. The latter service was attended by over 500 people, including many PRR officials. Burial was at the West Laurel Cemetery in Ballakinwood, PA, at a gravesite he shares with his wife, Mary Crawford, who died in 1940. Regardless, Dudley's death was a shock to the PRR and the local community where he had attained a legendary status. His eventful life was recorded in the New York Times, Philadelphia Inquirer, and numerous newspapers and technical journals. His legacy had just begun, however. And after his death, there were numerous memorials that were attributed to Dudley from, this is just a sampling of them. For instance, there's a 300-page book the American Society of Testing Materials wrote on the life and life work of Charles Dudley, including a biological sketch in the American Institute of Mining Engineers and a large headline in the Cincinnati Enquirer about the loss of a leader. However, I thought the most interesting memorial was a resolution adopted by the Foremen's Association of Altoona Shops, Pennsylvania Railroad. And in brief, it says that in the death of Charles Benjamin Dudley, this association has lost a member noted at home and abroad as one of the greatest chemists of the country. And further, that in his relation with his fellow members, his genial disposition and charming personality endeared him to all who knew him, and that the association was honored by his membership and mourns his untimely death. I think what's significant about that was his, views and attitudes to just the common workers, the guys that are actually doing the work in the shops, which was not always a pleasant occupation. This guy identified with them, and he was that kind of person. It didn't matter who you were, he would greet you with a handshake with two hands, put his arm around your shoulder and say, "Now, how are you doing?" That was the kind of person Dudley was. So in terms of the final roll call, this is the gravestone at the cemetery with his wife. And there are some lofty descriptions on this tombstone that were no doubt a tribute from his wife, Mary. However true, Dudley was too modest and humble of character to have written them. The Latin phrase esse quam videri was taken from a text written by the Roman statesman Cicero in 44 BC. It means to be rather than to seem, thus signifying true integrity, authenticity, character, and substance over reputation, appearance, or outward show. His epitaph, "To serve the present age, my calling to fulfill," was certainly true, but underestimated his legacy and influence over the next 100 years. So what was his permanent legacy? Well, certainly his contributions in Altoona and for the PRR were immense, but there were other factors at work here. What Charles and his colleagues learned in decades of applied science research, that serious problems plagued manufacturing. Business-to-business sales typically relied on ad hoc rather than general specifications. A lack of consistency frequently led to bitter conflicts between producers and purchasers, with both parties feeling swindled by inevitable variances in costs or quality of materials. So on June 16, 1898, Dudley brought together 70 people in Philadelphia to create the American Society of Testing and Materials. And this specification process is a voluntary consensus-based system where industry experts develop technical standards through task groups. It involves initiating a project, drafting the standard, conducting technical reviews and balloting, and achieving final approval to ensure product quality, safety, and compatibility. So what is ASTM today? Well, here's a picture of the headquarters building in West Conshohocken, PA, near Philadelphia. And it is the premier global nonprofit organization that develops and publishes over 12,500 voluntary consensus technical specifications. They're used worldwide to improve project quality, safety, and performance for all products and businesses and industry. So let's take, for example, your house. There probably isn't an item in that house that doesn't have an ASTM specification behind it. And I'm talking about everything. I'm talking about electrical wire, plasterboard, shingles, wood, beams, plumbing fixtures, furnaces, air conditioners. Everything you can imagine has been tested and specified by ASTM. And it's a product of these specifications are a product of years of research and collaboration, testing, interaction, and review of multiple drafts by a panel of academic scientists and manufacturing engineers. This is the same rigor and evaluation process of applied science that Charles Dudley had initiated and implemented 150 years ago as chief chemist of the Altoona Test Department. Currently, ASTM has over 30,000 members from more than 150 countries with international facilities and trade and international trade, and harmonizes standards through the participation of other countries and researchers. Now here's just a typical specification that I happened to come across. For the standard specification for welded austenitic steel boiler, superheater, heat exchanger, and condenser tubes. Now, if it seems as complicated and rigorous as the title implies, you'd be right. It's very complicated, but the people that have to make the product and buy it understand it. But it's interesting, under chemical requirements for steel, table 1, the first several columns say carbon, manganese, and phosphorus, and sulfur, and silicone. These are the same tests that Dudley ran in his steel rail study, and it's just interesting that some of the same types of ranges of chemical requirements exist in this product too. So this society has quite a history department on Dudley. You know, they see him as the founding father, and the president of the organization. And they said that this honor, this Charles B. Dudley Medal, was established in 1925 in honor of the first president of ASTM International, whose inspiring leadership had a profound influence on the organization's development. There was the 125th anniversary of ASTM a few years ago, and there's a quite extensive video of Dudley and his life's work. It's very, very interesting. So what was his legacy in terms of his life and his life's work? And if we look at it from a broad perspective, his legacy will extend far into the future as long as ASTM exists. His accomplishments as PRR chief chemist and his civic contributions to the city were important during the growth and development of both. He truly put the standard in the standard railroad of the world. So when reflecting on 250 years of Blair County history, it will be difficult to find a citizen who had the impact that Charles B. Dudley had on the city, and as the PRR Altoona, scientist to the nation and to the world. Thank you. Any questions, comments? Okay.
You did so good. You don't got any questions.
Well, maybe it was too
Thank
much.
you so much, Morgan. Oh, we actually do have a question.
Some physical disabilities from the ward with the limb. What do you know about that?
Well, it's a little vague.
Okay.
Some said he was crippled for life at the time, and then said I think his wife said he was severely wounded. But I think he must have walked with a cane at the minimum. He certainly wasn't in a wheelchair. So I mean, I think he got around, but I do think there was a lot of pain there too, as far as that goes. So,
Didn't slow him down.
yeah, didn't slow him down.
Not in the least.
No, remarkable guy.
All right. And with that, thank you all so much for coming tonight. Safe travel home. And again, if you enjoyed this presentation, we do have many more lined up, including Mark presenting again later in the year on the water system and for the Pennsylvania Railroad here in Altoona. So if you have an interest in that, Mark will be giving a presentation on that later in the year. Make sure you follow our Facebook page to keep up with that. And with that, thank you all so much for coming again.
Thank you.
Thank you.
Thank you.
Well done.
No, thank you. I can send this to you if you